Okay, so hi everyone, welcome to anyone who's new. This is meeting number 7, I think, the Open Source Drug Discovery Network meeting for Nsp13. And the agenda is posted up on the GitHub, which hopefully everyone's got a link to. I'll just post it here in case not. Right. So I'll get started. I'll get started with the SPR assay, I guess, because that's where most of my time's been spent. And it's just something that I was hoping to discuss with. Apologies. With Sumera, sorry. So. I'll just give a quick background because I know some people are new to the call as well. That might be helpful, actually. So this was the current workflow based on Costa's work running the generative modeling. So we have two sets of molecules at the moment that we're working from: the enamine real space trained set and the de novo generated set. So the enamine real space library consisted of 150 molecules, which were the top scoring list based on glide docking scores, and were then subsequently filtered based on log-D and molecular weight to kind of filter those down. That original list looked like this, and the dark green compounds, the ones we received enamine quotes for and were sent off to enamine, and all the other ones, the greens and the yellows and the reds, were ones that we would ideally need to get made or ordered if possible. And then the coloring corresponds to the score. So the red is the more negative scores, the green's the less negative, and the kind of network there is based on structural similarity. We got these 51 out of the 55 that enamine gives quote for. 51 out of the 55 were successfully made. Sumera tested 2 of those compounds via the ATPase assay, which showed some activity, and that left 95 compounds which still need to be made, and those are here, which they're a bit small to see, but I will share the ChemDraw file after the meeting so everyone can see those. Some of those made less structural sense than others, so particularly those with a lot of N-oxide para-nitro functional groups. But there are a few compounds in there that I think are synthetically accessible, and so I'm trying to pursue those at the moment as well. But obviously, if anyone wants to have a look at this list and see if there are any compounds in there that we could make, or either potentially make changes to without affecting the glide score, then that would be useful information as well. We then have the de novo generated list. So these are the original compounds, and as you can see, a lot fewer of these are accessible from enamine. So this is the list where I'm spending the majority of my time in terms of accessing the chemistry here. So there's 100 compounds here, and you can kind of see that there's a bit more diversity in terms of where the low scoring compounds are. So just for some
Tom, do you mind if I interrupt?
Yeah, sure, go ahead.
So we have some data back for N-oxide series compound, not a great, but we have some starting point. So in
Okay.
that case, did you compare with that compound versus all the leftover compound like you have planned for synthesis in terms of interaction or docking score? Because I don't get that response from Costa yet. So I'm asking you, did you compare before synthesis?
No, so not on the docking. So I have docked a few of the N oxides. So I've docked these 10 specifically. And it's not completely clear what the interaction of the N oxide is because the binding mode varies depending on the compound. There does seem to be some interaction with a tryptophan residue. If I skip down here. Yeah, residue 506. There seems to be some hydrogen bonding there. Make it a little bit bigger. Sorry, I can't make this image larger for some reason.
Anwar, are you saying that we've got experimental data back that might change the compounds that we're interested in? Is that what you mean?
Yes, kind of, because I'm thinking before investing time and resources for synthesizing this additional 90 compound, can you wait for crystallography data or confirm our N oxide series heat? Because that will give us a confidence of our docking and our current strategy, basically. Because some of the compound really complex and multi-step to synthesize for this series of molecules, right?
Yeah.
Just remember that we are, so in addition to finding good compounds, we're also interested in trying to answer a question about which method the Costa used was better. And sometimes these questions, mean that we make compounds that may not be a priority for the drug discovery, but which might be useful for a PhD.
Okay.
Right.
Yeah.
So there's two things going on here. One is synthesis of compounds for the sake of it, not for the sake of it, to answer a question. The other one is to advance the project. However, if we get data which suggests that a certain motif is being prioritized that doesn't seem to be helping, then that's significant. So yeah, we would act on any crystallographic data. Yeah.
Yeah, I mean, you answered my question really nicely because I don't pay attention with that part, as a whole PhD project. Yeah, that makes sense. Yeah, so yeah, that will also interesting to keep in mind, like our existing data and how we are getting the compound response from 51. So that's very small set of molecules, but we have something there as well.
Yeah, you raise a good point, and I think that's kind of why we've been prioritizing the SPR to analyze this set over the synthesis here. I think because we already have, I mean, all of these compounds that you sent from enamine contain the N oxide motif, and they're not that structurally diverse from the ones we're trying to synthesize in the other set. So I imagine getting the SPR for this set at the moment probably takes priority over the synthesis of the new set.
Okay, yeah, that makes sense. Yeah.
I was just going to say, I think Anwar makes a good point, and I guess it's marrying those two, right? That Tom needs to do his PhD, as well as following up the drug discovery aspect of the project. I guess the hits that we have at the moment, how much cheap SAR is there possible with analogues of those, compounds without the N oxide, for example? Really simple stuff. And I guess, what's the quicker task to wait for the X-ray structure or just order a bunch of analogues potentially?
I'm not sure if Costa was going to be doing some SAR analysis on those analogues. Does anyone know if? I don't know. Is Costa?
So James, Anwar is at risk just making some like 4 or 5 simple analogues of the 2 that were initial positives. In part because, first of all, I've cautioned everyone not calling them hits because they're active in one assay. We don't have confirmation in an orthogonal assay. But given that they show activity in an assay, Anwar is actually trying to do like swap the two ends around and make it without the N oxide and just resubmit it to the assay and see if we get if we see robust activity in a close analog, then I think we can dive a little deeper into them.
Yeah, exactly.
But right now, I call them compounds of interest. I'm being cautious. I'm not calling them hits at this point.
Okay. Yeah, that's fair enough. Again, I think having more than one compound in a series and having clear SAR, I guess that's what I mean, is that the more compounds we can find that are similar looking, and you start to see, distinct SAR in the assays, as well as getting your X-ray structure to confirm it's binding in the site that you think it's going to bind. That all gives you confidence it's a real hit and it's not just, an assay artifact, which sometimes happens sometimes.
And I did get an update from Joe Newman last week. He has soaked the compounds that we sent him in the crystals, and so he'll know in the new year whether or not there's any electron density in there or not.
Okay. Hopefully that'll be a New Year's gift for us all.
Have any of these compounds shown binding, or is this just a blind crystallography experiment?
We have some activity in the SPR, but we don't have a positive control in the SPR, so we don't know. We don't know if it's real or not.
But these compounds are shown up in the ATPase assay and the SPR assay, right? Is that right?
That's not all the time right. Some compounds showed ATPase assay activity, some compounds showed SPR. So we don't have real linear correlation between them. So we don't know what's happening there.
Okay.
But altogether, we have some activity among these 51 compounds. So that's the indicative that is we might have something.
Yeah, I'm trying to work on a positive control for the SPR here, but it's not as simple as I thought it was at the beginning.
What about magnesium and ATP? Would that work?
So I'll just skip this because we're on it anyway. So I did try AMP-PMP, which Joe crystallized with Nsp13, but couldn't see any binding. And that was with magnesium. I'm not quite sure. I'm not quite sure why that's the case.
P and ATP don't show any binding by SPR. They come off and quite fast, and their response to nodes are very low. But the other control, I checked it briefly, it's working very well. So from next onward, we will have a control for SPR. The Pucillegen, it shows very nice binding by SPR. So we have a control for SPR from now onward. Yeah.
The other thing you may try is an oligonucleotide.
Yeah, me and Matt were discussing that earlier this week.
Sorry, I'm new to this forum, so.
Oh, okay. So, yeah, there's that was a discussion we had last week. The other one we have tried is this compound. This we call it PUG, and that was confirmed as a nanomolar binder, but the binding's irreversible. So I'm just currently scouting regeneration conditions for this. To potentially use that as a control.
Samira, what was the compound you mentioned? Sorry, as the control.
The PUG.
This one.
Yeah.
This one.
Yeah.
And are you getting it? Are you getting the compound off somehow?
Yeah. I got the compound off.
How did you do that?
I just run it for 60-second K on the association time and then 120 dissociation time, and it was nice. Like I get a nice curve for it.
Okay, does that make sense, Tom? Sorry that I'm
So what was your dissociation time?
120, 60 and 120.
120 seconds.
Yeah.
Okay. Yeah, I mean, I've seen when I've run the Synthgram. I mean, you can see in this one I've run it for 500 seconds. I'm not seeing. not seeing
So
dissociation. And in the paper that I found this, I think that I actually contacted
yeah,
Professor Lin, and he said that he had trouble finding the right regeneration conditions to get the compound off.
I just run it. I haven't optimized it, but I run it as just to see that how it behaves, and it behaves like it shows a nice binding. So at least going forward, we will have a control for Nsp13. We can say we can compare this one with our compounds that it's working or not. So it's like that. And for this your experiment, I'm not sure. Like you tried 500 second K off, and how much time you run it on? 60 second, 200 seconds.
60.
60. I think here, like you have, it's the streaks, they are coming from, there is some problem in the buffer. There might be, so if you run it again like try it again, and what the highest concentration of compound you tried here?
So I was working at just above 200 nanomolar.
200 nanomolar, then shouldn't behave like this, but you can try a concentration like before. For optimizing it, you have to try from high to low, like 3 set of different concentrations, and for each those 3 sets, like 5 points each, then you will reach a conclusion, and I think you will get a very nice curve for it. It will show.
Okay.
Yeah,
Okay. Yeah, thanks. That's
no problem.
yeah, it's interesting because when I spoke to Professor Lin, he said that they were seeing the same thing. They were seeing the irreversible binding, a range of concentrations, and then had to go with glycine at pH 2.5 to remove the PUG from the protein. But you're saying it's coming off, so I don't know why there would be a difference.
If you can share protocols offline just to make sure you're doing the same thing, that would be great.
Sure.
Because that would be a very valuable, obviously a valuable result if this compound is actually okay.
Is the protein construct the same that you guys are using?
Yeah, we supplied protein, the same protein
Okay.
to UCL. Yeah, that's good.
Thanks.
Important.
Exactly the same. Wasn't made with a.
Actually, Sumaira, when you ran this, did you run it with magnesium in the buffer?
Yeah, I run it with the magnesium.
Okay, maybe that's the difference then, because
Yeah.
when I ran this originally, I wasn't using magnesium in the buffer,
Yeah, that must be the case.
and I'm not sure if they did in the original study either.
You
So
had,
maybe,
yeah, you had EDTA in the buffer,
yes, yeah,
so that answers your question as well. So it might be, even if you don't run it with magnesium, you might be able to see something, but EDTA, so EDTA is a chelating agent, so it's like,
yeah.
so Nsp13 active site.
So you're running without EDTA and with magnesium.
Yeah, without EDTA. So you can try 3 set of experiments, run with EDTA to see and compare how it behaves, this compound. 1 buffer with EDTA, second without EDTA, and third with magnesium. So
Okay.
like that. Yeah. So
Great.
then you will see the clear difference.
Okay, yeah, that makes sense. Yeah, so
But that's exciting, Sumaira, if you manage to get this to work as a positive control. That'd be a
Yeah.
big step forward for us.
Yeah, it got excited too. Yeah. Thank God we have something from now on.
Presumably you're able to regenerate it and then add it in again and regenerate it, right? So you can do it multiple times. Can you? So if you when you take it off, the protein is still fine, and then you can put the PUG back in.
Yeah. So how the principle of SPR is, like we run multiple concentrations from starting from higher to lower, and it goes on and off, like at least 5 concentrations. So it showed
Right.
in my case.
So the
Right now.
protein's still fine after you wash it
Yeah.
off.
Yeah.
Okay. Right. Great.
Anything with Sumarin?
Just Tom, just by way of intro, given that we're talking about assays, just there are so some other people on the call got in touch with me, Juliana, and got in touch with me about offering assays for coronavirus proteins, including Nsp13, and mentioned that they run, I think, that the ATPase assay or the unwindase assay. I'm sorry, I forget which one it is, but not the SPR assay. Juliana, did you want to say anything about the stuff you're doing briefly on assays while we're talking about assays? Because we're working quite hard to make sure this one works as a primary binding assay for molecules.
Matt, this is Daniel here.
Hi.
I guess she's just went to do some she's running some experiment in the lab. She's not online actually. Natalia is also here. Natalia, if you would like to say anything.
Got it.
Yeah, everyone could listen.
Yes.
Yes. Oh, okay. My name is Natalia. I'm a postdoc at the University of São Paulo here in Brazil. And I work here with my partner, Luana Mourão. She is at the meeting too. I work here with Helicase from Zika virus and SARS-CoV-2, 19, sorry. And we work here with enzymatic assays to know if some compounds could influence in both helicase activity during the virus replication. We have two kinds of assays here. It's the ATPase assay, where we can see if any compound could inhibit the ATPase activity of helicase. Yes, if the compound could bind into the ATP site, this compound could inhibit this enzyme activity. And we have another assay that is the assay where helicase could open a double exchange of RNA, okay? We have this double exchange of RNA here at the lab. We put this double exchange of RNA that have a fluorescent dye and this double exchange, and we can see if when a compound binds to the protein, if this compound could inhibit the opening of the double exchange RNA dye. Okay, can you understand what I tried to explain? I don't know if Luana has a photo. We can see how the assay works. I think that I just talking about the assays are really difficult to see how it works. But it's two kinds of enzymatic assays in solution.
You are talking about the principle of ATPase assay and DNA unwinding assay, helicase assay. So we have already ATPase assay running here. We are already testing our compounds through that. And the unwinding assay, we have another partner from UNC, Ken, his lab is working. And then I just developed that assay, it's in the final stages, the DNA. I'm using the same principle you said, like fluorescent labeled DNA, double-stranded DNA, and then just use Nsp13, and you have a quencher to unwind that double-stranded DNA. So we are working on the same principle for both of those assays for Nsp13. It's nice to hear from you.
Oh yes, and have you already used these compounds in this assay to see if they work?
We already tested these compounds by ATPase assay, but unwinding assay, no. As I said, that it was I was working just over this weekend over that assay. So we will start running those, testing those compounds by next year. All the compounds we already have, and the next all compounds by unwinding assay too.
Yes, another thing that I want to say to you is why you use SPR assay to know if the compound bind to the protein and not use another kind of binding assay. Here in our lab, we have a micro scale thermophoresis. Have you already listened about this technique?
Yeah, I know about micro thermophoresis, and we do run here thermophoresis for different proteins or targets. But for Nsp13, we are trying, one enzymatic assays, and for orthogonal conformation, we don't want to miss anything. That's why we are trying SPR. Like thermophoresis will be the same. It would be like something like similar, like enzymatic or that principle. So we don't want to miss out anything. That's why we are checking with SPR too.
Yeah,
But if it don't bind to the active site.
So same thing at UCL. We have MST at UCL, but it's quite slow throughput by comparison.
Yeah.
So we haven't used it really.
Also, I
Okay.
think SPR gives you interpretable biophysical parameters. You get the K on
Yes.
and K off, whereas
Yeah.
MST, it's always an interpretation. The shifts, you assume that they tell you something, but you don't know exactly what they tell you. I think SPR really measures directly something biophysical.
Oh, yeah. Okay.
Yeah, the other comment I want to make is it's crucial to have enzymatic assays and binding assays. I'm saying this as a veteran of many disappointing screens for helicases. There are many ways to inhibit helicases that don't involve binding to the protein. They involve somehow interfering with the DNA in some way. You get a lot of false positives. And so you must have to not just orthogonal assays, but one assay that clearly measures binding. And it's important to have compounds that behave nicely in SPR, so that have a K on and K off at this stage.
Yes.
Because there are a lot of things that just stick to the protein and pretend to be inhibitors.
Okay.
Thank you for your input. Thanks.
Okay, great. Sorry, I interjected, Tom, but if you wanted to carry on with the SPR, go right ahead, unless you're done.
Yeah, I think that's mostly everything, other than say that the biotin capture's kind of repeatable now. Had a little bit of a struggle with the repeatability at first, but it seems to be working fine now. I haven't kind of cross compared methods, but I assume Sumer's using the same protocol for the biotin capture.
I presume it's 5 micromolar protein, not millimolar, right?
Yeah, micromolar. Yeah. Yeah, sorry. Yeah, so I think obviously that's where the priority is, because I'm trying to get these compounds screened by SPR so we can get them to Joe. Sorry, I don't know if I missed it, but are those compounds going to Joe regardless, or is it the same set that we would be sending, that we have here?
I think they've gone. So
I just put in the notes that Anwar can share the list of compounds he sent to Joe.
I sent 20 compound, that is not 50, like not all 51. So it's a mixture of 14 compound from BRR2 and thiazole series and 6 compound from this N-oxide series. So I selected based on the activity, either on ATPase or SPR. So those 6 compound has some kind of activity. So that's the story. I'll send you the Excel spreadsheet. Yeah.
Okay, great. Thanks. Yeah, so I just quickly covering the chemistry for the de novo list. So this is the top 10 list, and the circled ones are the ones that I'm currently chasing in between all the SPR stuff. Obviously trying to get number 1 out as quickly as possible was the priority, just because it's the lowest scoring on both lists. So I managed to get to this amine on 150 mg scale, and then tried a couple of coupling conditions for the reductive amination, but haven't had any success with 2 of those methods. So the titanium induced amination. I tried upping the equivalence of titanium to kind of push it forward, but all I was seeing was kind of the reduced N-oxide pyridine, and not any product. So I suspect probably what's happening is just the amine is just kind of chelating to the titanium and just stalling the reaction there. So I have this one last method to try and offset the amine and then try and reduce that directly, but I've needed to get more material through. So I tried to make just over 2 grams of this, and it seems to be clean by LCMS. It's I'm just having trouble getting it dry, so removing all the solvents. I think so. I've tried kind of heating that and using kind of aqueous mode on the Biotage V10, but even that's not getting it off, and sticking it on the high vac all day is still not removing all the alcohol solvents. So I think I'm going to try freeze thawing it to maybe try and get rid of the alcohol. But we were talking about this route earlier. I think if I have to move away from the reductive amination chemistry, we're unsure about this kind of alkylation step. Obviously not just because over-alkylation is a problem, but as Matt mentioned, possible E2 elimination to kick off the iodide and end up with the alkene. So I don't know if that's the most sensible route. So the next best option that I can think to try would be a Mitsunobu with the alcohol. So we have some of the alcohol already in the lab, and I'm just wondering about trying that as a backup. Obviously we're not dealing with chiral alcohol here, so we're not worried about the stereochemistry, but it's the next option I think to try there, unless anyone's got any other suggestions. But since these two compounds are essentially the same apart from the methyl group, I imagine the chemistry that'll work for one will work for the other. So I'm hoping to try the Mitsunobu once I've got that amine dry. I was hoping to get it done today, but we've got snow, and as soon as we get snow here, it means the trains start working. So I'm currently stuck at home. But as soon as I can get in to dry that amine, then I'll try the Mitsunobu and see if that works. And I've got the chemistry for the fluoropyridine acid from Anwar. I've got the route from Piramal, so I'll be trying that once that protected amine is made. This was the suggestion from James, so I've ordered the starting material to get on with this chemistry, but this is just essentially acylation, catalyst rearrangement, and then Schmidt reaction to get this benzyl protected amine down here, and that's for hit number 5, I think. But these were one of the non-purchasable building blocks that we were looking at trying to get routes to. So I'm happy to get this on as well. This was a backup route, so I think so. This has been published in a patent, so I'm hopefully quietly confident it should work. And the beneficial one with this one is that the starting material comes with the right chirality, so I can get the correct stereochemistry of this route. It's a bit low yielding, so it might be worth swapping out the EDCI for something a bit more punchy. Probably try like PyBop or something, and then reducing the amide. But obviously, hopefully shouldn't affect the BOC group, and just reduce the amide. And then finally this one. So this was another one of the building blocks that wasn't purchasable, and so I've ordered the starting material for this one as well, which the simplest route I can see to this is SN2 to the nitrile, and then lithyl reduction to and then BOC protection to the BOC protected amine, and then this kind of Mitsunobu reaction kind of resembles a kind of Gabriel synthesis with that hydrazine. There's a couple of more experimental routes that could work as well. So I found this nickel catalyzed reaction of direct conversion of nitriles to rock protected amines. So that's a potential backup route. And then obviously a one pot Mitsunobu and Staudinger from the alcohol to the amine salt. And then if none of those work, then there's also an Apple SM2 and then Staudinger reduction as well to try. So I think there's a few different routes to get to this building block to try as well. But yeah, I was hoping to get into the labs today and get that done, but I'm stranded, unfortunately.
So Tom, are those key building blocks required for just single compounds, or are they to make a whole series of the top scoring compounds?
So these are individual building blocks for individual compounds.
Okay.
But obviously, I think because they're key building blocks for those compounds, and essentially the only variables on those are the N-oxide amide coupling and the amide coupling on the other side. So if any of those do turn out to be hits, then we have routes to those building blocks that we can then vary.
Tom, I may have missed part of the discussion, but I'm just curious how different these hits are from the nearest neighbor enamine molecules, and knowing that enamine thinks they could make everything in their collection like 2 or 3 steps, whether that would be helpful in any way.
It would be. I mean that's part of the conversation about trying to prioritize the enemy list, because a lot of these compounds are quite similar. So especially in terms of having that N-oxide and the 5-fluoropyridine, a lot of the enamine and de novo compounds have those 2 motifs. So getting those screened by SPR would be probably more important. But the funny thing is, enamine did say they could synthesize the top right compound, but then none of the rest. So, but given how similar they are, I didn't quite understand why that was the case. It may be that the building blocks are the problem, which is why I've been trying to find routes to the building blocks.
Yeah, I don't think we have access.
Sorry, Alex. In each case, the building block is the chemically interesting bit, and if we get that, then the rest of it's straightforward. But at the same time, Tom's been in touch with Kostya to try to see if a molecule can be generated which is structurally similar, or gives a similar score without the complex building block, right? So those 2 things are going on at the same time.
Right, you mean that something that comes to your independent synthetic brain, we could score before you make it. That's what you mean, right?
Yes. So it's a lot of, it's a lot of effort to make one building block for one compound if in the end it doesn't perform very well. So you have to trade that off against the potential advantage of actually, getting a nice compound. But if there is an alternative which doesn't have this roadblock, then we should try and find it. So the idea was to keep everything the same in the molecule, apart from that one building block, and see if Kostya could find something generatively that didn't suffer from such synthetic trickiness.
I think that's a good way forward. I mean, because for example, for the pyridine acetic acids, which are common in many of these compounds, there we just invested in the chemistry time at Piramal to make it, because we knew it would go into multiple compounds. It gets harder to justify when you're having to do multi-step synthesis to make one building block for one compound, given the chance that it probably has, only a 1 in 10 chance at best of actually being active. So.
I guess we may be talking about like 2 different strategies that can be executed. The simplest, as I see it, is that as you look at molecules that are high scoring, but you find them difficult to make, you could think about some close analogs or building blocks you could use, and we could then score those proposed compounds before they're synthesized. That's one approach, which is quick. I think, Matt, the alternative you may be talking about is that we could bias the pre-existing or fine-tune the generative model we already have to start making molecules that are similar to the desired compound, and the generative model may spit out some alternatives that will score high. And then you could look at those and see if the model has generated new structures similar to the desired hit that are easier to synthesize.
Yeah, that's right.
Which is sort of what we do anyway in the process of model building. That's part fine-tuning as part of the design, but we could fine-tune on molecules that we have or the system has generated, or we could fine-tune on the molecules that you give us as potentially useful candidates and synthetically feasible.
All right.
Either way.
Yeah. So
just wanted to clarify.
So both of those are relevant. It still remains that an interesting scientific question for Tom that he's addressing now is which method is better, right? Is it the docking or is it the generative model, right? So we need to remain in those two camps.
No. This is so there is no generative model without docking. This is not quite accurate. So just to clarify. And this is sort of the, it's the curse and as the advantage is kind of both, right? So we're restricted in what we do to the quality of scoring functions used in docking. The generative model that we use is to expand the structural diversity of compounds that can be scored highly, but the model with which we score anything is based on reproducing docking scores without actually docking. So in other words, generative model is inseparable from docking scores. We use generative model in order to diversify chemical structures, but when we score them with effectively a not cooked up, with a model that reproduces docking scores. And when it's small number of molecules, then we could dock them for real.
Yeah,
but it's not separate, right? It's not that the generative model produces something totally independent of docking scores. Not in this context, not in this exercise.
Sure, but it's still
so I think we all agree that we need to make the molecules to validate the approach, right? So
right.
I think right now there's probably a limited number of the multi-step synthesis building block that Tom will have the capacity to make.
Correct.
Right? So I'm not saying don't make any of them. I think we should probably say let's make some of them, but then take the ones that don't make that list, right? And rerun the generative model, and then Tom can look at the output and say, actually,
exactly right.
I can now make 10 compounds instead of making 2 compounds to test the model, because all of these come out of the generative model, and some of these will be more maybe 2 steps to make the building block and not 5 steps.
Generative model may help find alternative structures and alternative building blocks.
Exactly.
That's
right. But it'll be an iterative process where that require Costa to rerun the generative model, show the compounds to Tom. Tom say, yeah, I'm going to make these.
It's
10.
not really a rerun. It's fine tuned. That's what the term that we use.
But yeah. Fine.
Yeah.
But it would be nice if a compound is suggested, which is good, and we look at it and we try and make it, and it turns out it's a pain, to be able to come back and say, actually, could you just get rid of this bit, please, because this is screwing it up. That would be great. We don't want molecules necessarily that we can just buy, because we want to also be chemically useful.
Oh, absolutely.
Which you can't buy, right?
Yep.
So it's not a problem that we can't buy it, right? But at some point it gets too complicated. Yeah.
And I mean, doesn't exist to kick you out of your jobs. I get it. By the way, as of today, we have a name for the method that we use. It's deep accelerated docking with fine tuning. deep accelerated docking with fine tuning. It abbreviates as dead fit. And that fit, according to Urban Dictionary, means gorgeous.
That feet.
You know, I love inventing terms.
Okay,
That's the new term.
So Alex, will
So call it that fit.
Kostya or someone in your lab have enough time to iterate the loop with Tom?
Yeah. It's just doing what we already do with different molecules that we show to the model. It fits squarely. So Kostya and James will work together. We just need synthetic or structural, not synthetic, structural ideas transformed into a drawing or smiles or whatever. That's all we need. It's pretty much the same loop that we already have. Right now, we show to the model compounds that are enamine or previously generated molecules that are high scoring. Instead, we could show molecules that come straight out of your mind. So it's human in the loop, essentially. That's what it's called.
Yeah, I think just on that point, I mean so I'm just looking at the list of compounds that Enamine said weren't makeable, weren't synthesizable. And one of the things that might be a good starting point for this is to look at the compounds that have the para-nitro groups to the N oxide. It depends on timing, right? Because we're kind of relying on the data from the N oxide SPR screening and crystallization to tell us whether the N oxide is necessary or not. But one suggestion I was going to say was maybe trying the same list of compounds either without the nitro or without the N oxide and seeing how that affects the binding scores. Because I imagine once you knock that off, maybe they become a lot more accessible. Just because it's an unusual motif that I've not seen before.
So those are generative compounds, right?
These are from the Enamine real space.
Okay.
So these are
I see that they have
from
sort of the higher, close to the highest scores we got out was close to -8 for Nsp13.
The lowest scoring on this list is -8.39.
Yeah. But I mean, like overall, that's the range of scores that we were getting.
Yeah.
So are you picking up any of those as most interesting for you?
I mean, obviously the lowest scoring.
Or are you thinking about like something similar with a different building block that you could make easier?
I don't know, it's a tough question.
Because so there are two options, right? The easiest is that we may have made it already, right? So we could mine what's been made with whatever you draw. Second is we could score it, dock it, score it, and then depending on the result, make it more or less interesting. Tell you what we get. I mean, I think that this iteration would be really unique exercise.
I selected 3 compounds from generative list, I think, to send pyramol. Each of them will take 80 steps to synthesize. Even the problem is
8.
Yeah, I can show you the slide.
Wow.
It's so exotic linker in between. It seems like FASTA is very simple chemistry, but practically it's not. I can show. Let's see.
Wow.
Yeah.
But so, you don't want complex stuff, right?
Yeah, we don't want complex stuff, but it's unfortunately complex. So initially I proposed simple synthetic scheme, but that didn't work out in a way I can show you what happened there. So now we improvise in a way that is going Mishinobu kind of reaction to have this building block move on. Another big problem here is the linker is not UV active, so you cannot track it, what is going on and the next step reaction. That's why we need to have something to carry on a step and to purify and to characterize altogether.
And the final molecule came.
Is this one?
That's the generative molecule, but that came from generative model.
Yes, that's right. Yeah.
Like exactly. No intelligent modification.
No, that's straight from the list.
Yeah, and that's also another thing. I selected 3 compounds. That's also from my eye. It seems like easy to make, and I checked all the precedents how to make. So and afterward is in practical sense it's not that simple. So even making this building block, it also takes 4 steps to synthesize. One of the example is here. I can show. Okay, hold it here. So this conversion is very pretty easy conversion. It's supposed to work, but for pyramol, they couldn't make it after several trials. So it basically reduced to alkene, and that happened. And that's why we had to go another route to synthesize this building block. This is our 3rd compound to make it. It's very simple. I thought I can make we can make this linker 2-3 steps, and that's the 3 steps. But practically it didn't work out. So now we have to go in 80-step reaction to make this compound. So that's why I asked that question very beginning to Tom. That is, instead of diving in too much complex chemistry, we need some indication that is this kind of compound really working in that way.
Yeah. No, I do agree with you, Amar.
Yeah, I'm wondering what is the nearest neighbor in enamine library, because that's what we always do. But I think it's useful to have that side by side every time we do this analysis of synthetic feasibility.
Yeah. I mean, in the plain look, it seems like very simple molecules. The problem is the linker in between. It's 2 amide coupling. It's really nice, cool thing. You can do it anytime. And the problem is in between linkers. So that's not really commercially available. So that's why right now that's why right now I'm making the top heat so far right now. We cannot say heat. It's not confirmed heat, but I made that compound. That's pretty interesting chemistry, very simple. So if we can reproduce the activity for that compound, the SAR and further development will be really easy and tolerable.
I mean, I think it's totally exciting that a molecule generated totally in silico with no synthetic intelligence, because our models have 0 of that, right? It's still makeable by a chemist. For me, at least, it's highly exciting.
Yeah, I mean, some of the generative compounds I've seen.
Yeah, Alex, we can make everything.
Actually looks like they're makeable. So.
Well, I know, and it looks different because, every paper I've seen and every criticism of such papers I've seen is that you guys are total nonsense, because eventually what your generative models produce is something that's easy to make, and it's a close analog of serotonin. So this is actually great.
Yeah, but you started from real, which is makeable, right? Yeah.
And Campbell, right? The other model strand of Campbell.
And Campbell, yeah.
Anwar and Tom, if you send structures of those you've picked, I'm still interested in finding closest enamine real space compounds, right? Because those are supposedly makeable in 2 or 3 steps. I think that's the claim from enamine, if I'm not mistaken. And somewhere in between, we might find in between the generative hit and enamine, we might find something that is easier to make, still novel. And I think looking at them side by side is helpful.
So in that case, Alex, I have this question for a long time in my mind. So what is basically our will be standard workflow between you and us and biologists? Because we'll make the compound, we'll send to biologists, they'll give us data. Then how we'll send to you, when we send to you? Is there any standard
Elmer notebook?
It's there. and it's there, nobody even log in there to check what is there. So I made it as much fun as possible in the notebook.
Yeah, no, I think we need, as far as data exchange, I think we just have to commit, all of us, to using the same notebook. That's the most straightforward way of sharing the data. And we could, you know, Renzi could come up with all sorts of alerts, right? When the relevant data to a, it's like an email notifier, right? Or Google search notifier. I think we could do that.
Yeah, so so that this question I asked before to Kosti as well. That is, I have the small feedback of data. So now I need to know at least what is your insight on that one, or you think about this compound from your docking perspective, how we can advance in future.
We could, Anwar, I think we like between our groups at least, as sort of guinea pig of this entire process. I think that's what we need to establish, right? So you put the data, we just need people who do screening, right? Commit to the same. As soon as they screened anything, they need to learn how to put the results into signals, right?
Yeah.
But that's that's research data management in action, right?
Yeah, that's right. Yeah.
But as far as research, I think it's the interplay between generative compounds and purchasable compounds and synthetically makeable compounds, and that's what I think we're exploring functionally right now, like how to make that loop work.
Yeah. So because I'm really worried for future, because Piramol is already running out for a chemistry plan at this moment. Will be done by mid of January. So far, what chemistry we have. So I need some solid ground and solid workflow between us, biologists, and computational thinking, so that I can move really faster and efficient way. So that's I'm trying to figure out and making a smart workflow as much as possible. So.
I think we've reached time, or just slightly over.
Yeah, and I have to go to student defense. So.
I thought it was at 6 p.m. for a second. I was like, oh God, Jesus. But forgot that time difference.
You guys are eligible for a drink. Good to see everyone. Thank you.
Yeah.
Bye.
Thanks, Alex.
Bye.
All right. Thanks everybody.
Thanks, everyone.
See you next week.